Okay, so apparently it wasn't really possible. It wasn't really possible to run that game with so many at the same time and facilities here and linking up to wherever the server is in Denmark or in the cloud or so. But like I said, we're not going to close down those passwords. So if you think this is fun, you can do it some other time, maybe over the next few weeks or so, just to try it. It is a game, but it's what's called a serious game that illustrates and is meant to create awareness about the issues that often arise when you try to manage a river basin. I'll first go back to that exercise of yesterday on this Shira in Malawi to illustrate a few of the things you can do with your mic workbench. And then if time permits, maybe we'll run a few steps on the game just on this one computer, ending at 12 o'clock today. So this one was first to import data. This is already done, so I have some GIS layers here. And then I think to make a map of that, let me just try that. So I take the catchments that are there and add to a new map, which then comes like this. So these are all sub-catchments. Put the river on, so add to the active map, and some stations, which are these discharge stations here. So you can see where they are. If you generally in this, whenever you click on something, to the right you'll see changes in properties and in tools. So if I click on rainfall on a GIS layer of the rainfall stations, these are then the geoprocessing tools I can use on that particular layer. Season polygon you can actually calculate here if you want, and you can export to Google Earth and to shape files and other things like that. And there are also some tools other tools like that. If I click on the background here, then I get the properties of the map as such, and the background map can then be changed to maybe OpenStreetMap or so. If this doesn't work, I think many of you saw that yesterday, then it'll give an error message, and the details of the error message will tell you to change your projection to this Sodom Makata, and then it'll work. Similarly, if I click on the legend on these orange dots here for the discharge stations, then again this changes, and here I can then change, should this be orange dots, should it be another color? I like to use purple triangles for discharge stations for some reason. So I go down to purple, and instead of a circle I call it a triangle. And maybe instead of 7, we make it 10, so it's a bit larger like that. You can change things like this. So I think that's this one is just, make it like that. The legend is also on. So again, if I click on the stations here, I can here select the attribute to display, and there are different attributes in this. The ID 1 is one of the identifications, and then on the text, there is what is the color of the text, the font, and so on, but also whether it's visible or not. So if I make that true, then we can see the text like this. So in this way you can make maps, and that was the purpose of the first one. Then there's a statistics maps it's proposing here, and this is on the rainfall station. So if I add the rainfall stations to a new map, to a new map, they are here now. And if I select one, or right-click on it, you can see that connection with that map, we could have some documents, a spreadsheet, or a time series. And right now there is no time series. But you can associate a document. So if this is a gating station, maybe there's a document with information about that station. It was established in, 20 years ago, and it has, this is the rating curve and whatever. We changed the equipment in 2005. Information like that which can be useful if you're looking at the data and find out it's a little strange. Maybe there's a shift in 2005. You go back and see why is that, right? Or somebody else, if you're setting this up and you have a colleague working on that, then the information is stored with the station on the map directly. Here what we'll do is just to associate the actual time series. We have the rainfall over here, and if I label these stations with their name, so I make the text visible, then we can see what they're called. And we have the same names over here. So here's a station called Balaka, and if I take that with the mouse and pull it over to Balaka and let go, then there's an association between this point in the layer and that time series. So Bumwe is down here, and Chichiri is there. So I'm just associating all of these stations now. Chileka is here, Liwonde. And this is actual data from that area. Let's say this one I think is actually over here, yes. Closer. So let me just get all these associated. Mangochi is somewhere up here, I think, yes. Because once you have the association, you can then work with it in special ways. Mimosa comes here. And Chalo is not there actually, so we just skip that. And that's the way it is in the real life. No, I think that's missing, and Sanjay is somewhere south, as I remember. But often you have points may be missing, data is missing, data is wrong. There's all sorts of problems to see. And here, Enchö is actually called Enchö Nkande, right? Often you also see the spelling is not the same. So almost there. Chiolo is here, and Walker's Ferry is there. So now if I select the stations here on the list of time series and right click and say select associated features, then it selects all the points which are associated to these time series. And then I should be able to use, and some of you couldn't, but we'll try that. Statistic maps starting in January and make the average, say. If I run that, it's doing something. What it's supposed to do now is to calculate the average rainfall, which it then did, at all these stations, and then make a map showing what is the rainfall in a scale here. So you can see going from 0 to 14, that's the, in millimeters per day actually, that's the average rainfall at these stations. Some of them don't have any coloring because data is missing or insufficient to calculate this, right? But the darker blue, so we have very dark blue over here to the right, the darker the blue, the more rainfall, right? So this gives an indication of how is this distributed, and sometimes you can also find errors. And I think that's the next, once you've done that, try with a maximum instead. So if we go to the statistic maps, instead of average, we say maximum, and then run this one. And by the way, it starts with just the last year. You can change the period. So we'll try that also. We just have the last year here. But if we go down to 2000 in time, then it's like this, which is a little surprising. Okay. Maybe I didn't. In the data I gave to you, I put in one station which has a value of almost 10,000 millimeters. And then it showed out that the scale was from 1 to 10,000. One was very dark. All the others were completely white because they were very low, right? So as an illustration of a way of finding stations that are outliers or values that are wrong, right? So that just by this one tool with many stations at the same time, because are there any of these who have an unrealistic maximum? Since it's not in my data set, it looks quite reasonable. There's one here with 400, and this is daily rainfall, right? That happened 2015, where there was 397 millimeters in one day in this station here. But like that, getting an overview and keeping track of which stations are located where and where's the data. So that's the idea of this one. Then there's one here to compare discharge data. We have we go back to this map, and I just remove the rainfall. On the main river, let me just explain that. We have, up here we have Lake Malawi, which is part of this African rift that you may have heard of. All this part of Africa is expected to break off one day, maybe in 10,000 years, maybe in 100,000 years, but it's not very, it doesn't really stick very well to the rest of Africa. And Lake Malawi down here is has a surface level about 500 meters above sea level, but the bottom is 700 meters deep, so the bottom is 200 meters below sea. So it's really somebody's been there with an axe, and it's 25,000 square kilometer area, so quite a big lake. On the flood and drought portal, there is a data called GIAN, a GIAN satellite, and that measures the water level of lakes. And the measurement in Lake Malawi is perfect because it's so big. And I think also maybe the satellite may be passing north to south or so. So it gets many points on the lake. So in terms of the average lake level, it's actually better data than what we get from the authorities in the country. Anyway, if we look down here, water flows then out of the lake, and then it passes a discharge station here called 1B1, flows further down to 1P2, and further down there's one called 1L12. So these three stations, which are shown here also, are all on the same river, with the L12 being downstream. So if I make a chart of all these three at the same time, like this, then here we have time series from 1950 up until about now. And it looks a little strange in periods. If we can zoom in by just making a square like this. So here in the beginning, back in the 60s, we had only 1B1 and 1P2. 1B1 is the upstream one. And as you can see here, it looks like there's more flow upstream than downstream. Is that possible? I mean, we have downstream here in the dry season, we have down to 100 cubic meter per second, upstream 200. And this is these two stations here. I think we can measure the discharge somehow, or maybe not just now. But there's twice as much water upstream as downstream. And flowing out of this big lake and then down here, and then 100 cubic meter per second disappear. That would be a very thirsty irrigation area. And I know there's no irrigation in this area. So the most likely explanation is that the rating curve is just wrong. And whether it's both of them or one of them, nobody knows. This is back in the 60s, so long back, and maybe we don't need all that data. There's some relation we can see. Here it is more or less the same. Then both of them drop suddenly and come back up. That might be possible because there is a barrage located just upstream this one, which was constructed about that time. And maybe they are here, again it's falling down very quickly. They might be storing for a while and testing and so on. It was quite new, I think, here in the 70s. But it's not obvious, or from these graphs we can see something is wrong with the data in this period. Maybe it's possible to go back and see what were the rating curves, were there any comments from the people attending to them in the time. Can we find out which is reliable and which is not? If we move further up in time, we now get three stations, and the downstream one is now yellow. Can you see this? Which at least has higher flow than the others. So here we have a period which may not be so crazy. A period like this where 1B1 and 1P2 are more or less the same now, and 1P2 is higher, which you would expect, and even more in the downstream. So here around 79, 80, it looks to be okay. There's a peak A little strange, of course, that the peak comes later upstream than it comes downstream. But all in all, not so bad. We might be able to use some of this data. Then there's a period here in the middle, which is also a bit strange. We have the two downstream stations more or less doing the same, but the upstream one suddenly jumps down here, and then it has the same pattern, but it's about, 300-400 cubic meter per second less than everybody else, than the other two. Right? So here, 2 out of 3 are probably correct. So what we can do with this blue data is either throw it away or try to lift it by a factor and see, does it then look realistic, and then maybe use it and so on. But it's going to be uncertain, whatever we do, right? Then comes the good period. We have, let's zoom out again here. We have a period here from, let me see if I can get that right, from about 88 or so here to 92, say, where it looks quite reasonable. They are following each other. You have the downstream higher than the upstream, generally at least. Peaks are occurring logically and so on. So we ended up actually using those 4 years for calibration, discarding everything else in practice when we modeled with this one. I haven't checked, but I guess that there was some project in that area where somebody came and helped them look at their rating curves, check new equipment on the stations, getting everything in order. So when that stopped, sometimes here in the early 90s, it was okay. But then after that, again, things start to deviate. And here in the later period, they're sort of moving apart, right? We have the upstream blue one like this, more controlled now by the barrage, so it could be right. But then just downstream is the red one, which is now much lower. And the further downstream is just disappearing up in the, I don't know what's happening. So from a data point of view, a very sad story, this one. And I think the task was to find when there's a period that you can use, and that was these 4 years, basically. Rainfall. We have catchment rainfall are in here, calculated in different ways. We have this GPM catchment rainfall and also some daily catchment rainfall. And that is for a few catchments out here in the east, which I will just show on the map. So we'll take them the name and make that visible. Oh, sorry, not the name, the ID1. And let the map be, let the background map here be this Google terrain instead. So we can see how the elevation is moving, and I'll make it a bit transparent. So we're zooming in on these areas here. We also worked with them a bit earlier. So we have a mountain here called Mulanje, and then if I put on also the rainfall stations, you can see there are these 2 stations down here which are available to calculate the catchment rainfall. So both for all of these three catchments, we only have these 2 stations to calculate what the catchment rainfall is. I'll just make the legend a bit larger so you can see where they are. So 14C8, 14C2, and 14C7 is the name, sorry. And these 3 are all given here. And I think the task was, well, map them, yeah, like that. And then look at the daily GPM and compare them, and compare the daily and the GPM rainfall. So we have the daily rainfall, let's take maybe 17C2 here and plot that. And then let's take the same for GPM so we can compare. So now we are comparing rainfall. The yellow one is the GPM, and the blue one is the daily rainfall. And does this look like it's the same, or what? Of course, it's 2 different sources. One is satellite, and one is measured at rain gauges. Does this look comparable? No? But one reason why it's not comparable is that if you zoom in here, the GPM is available every half hour. So all of these are half-hourly rainfall. So here's 10 millimeters, 10.8 within that half hour, whereas the blue ones are daily. So you can't really see what it is. But there's a trick for that.
Is it added up of this?
If you add up the rainfall to daily, you can see it. And there's a tool for that. So if we take this one, there's a tool called resample, and also other tools like that. Resample to a day. If I run this to a chart, then now I get the daily rainfall for this GPM. And now I can take the daily measured and add to the active chart. Where did it go? Or I can take it from here and then move it to the existing chart, which is this one. And now we can compare here. Sorry. Now you can see the rainfall of these two, where the yellow one is the GPM and the orange is the measured by these ground stations, right? And there is some relation. When it doesn't rain, they agree on that generally. It's not, I mean, how high exactly it is varies a bit, but I think it's somewhat encouraging at least to see, particularly when you have high rainfall, that some relation is there. And that is in spite of the fact that the daily rainfall in this one there's only one station inside the catchment. And then I think we used that one also just to have a little extra. But you have the mountain areas and you have the lowlands, and we only have one station. And still, particularly when it rains heavily, the satellite and that looks similar. Right?
Suppose we have daily data of rainfall and we have to calculate the half-hourly rainfall.
You want to calculate what?
Half-hourly rainfall.
Half-hourly. Then you distribute it evenly throughout the day with 1 by 48 every, because you have no idea, right? But on this you have like this satellite information or other information like that.
Is there any tool to calculate this? No?
Divide by 48. I mean.
48.
Yeah, I mean, if you divide by half hour, 24 hours. I mean, there's no specific tool for that. Yeah. So it says here do the same for the other stations, but I think we'll skip that. And then I just start a game instead. But that was I mean, I hope at least for those of you who work with water data that you find this useful. There are lots of other tools in there that you can work with and explore as you move along. I thought, let's see if we can get a little further on the game. Oh, sorry, not about the game. So start on one of these Aqua Republica game, and then I'm going to ask you what you think we should do. Right? So now only one playing. Hopefully it goes a little faster, and hopefully my internet doesn't disappear, which it does occasionally. So we have about half an hour. Okay, so there's an introduction which I'll skip. We have it set up here, and I'll start by running a year right from the beginning. There is whenever you run it, there's some background information about conditions in the world, women and girls living without a toilet, spend so many, like that. So here are some objectives. We should develop 6 food farms and 3 cash farms. And please don't talk. So food and cash is apparently the objective here, and mainly for food. There's some background here. The Farmers Union has proposed to develop these 6 food farms and 3 cash farms. This should generate enough food and funds for the river basin. Water is needed for cooling power plants. Some power plants in your area are experiencing water shortage and are reducing production for that reason. Some of your farms are experiencing water shortage. This will affect the crop yield. You can click on this one and get ideas generally. Okay, so we better build something. And you can do that by clicking this one. You can build cash crops. So here's a cotton plantation, for example. It will cost $40 or whatever this is, probably $1 million maybe. It uses 2 cubic meters per second of water. It takes 1 turn to construct it, and some other information, well, how much power does it use and so on. Should we build cotton? We could also build groundnut. Cost $45, 2.5 cubic meters per second. It produces some food. What do you want to do, cotton or groundnut? Cotton. Okay, so we put a cotton plantation somewhere. So we put it here. Should we build something else? Some food? Give them some food to eat. So food, it could be sorghum, maize, millet, livestock. Livestock. You're not a vegetarian, huh? Cost 15, takes 1 turn. Okay, we put some livestock here. You want more food or more anything? More food. We are running out of money actually, but let's see if we're allowed to produce some more food. Millet? Yes? Let's see if we can do that. We'll still, but we won't create money till we run, but maybe we're borrowing money in the bank. Do you want to do more now, or we wait till next turn? Run a turn? Create some more? Run. Okay. Some background, what happens with floods, we'll skip that. Okay, a drier year than usual. Your river basin is experiencing a drier year than usual. Water availability has dropped. Check out the water bar. So we have the bars up here, and you can see now water reduced a lot. We have houses and other things, but water is quite low. And these are indicating drought. So the forest here is suffering, It's possible to do something. If we take our cash farm here, which is a cotton plantation, if you click on this one to the right here, you can implement some policies. Right now, nothing is implemented, but there's one called efficient water use. That will cost $10. It will not give you more cash, right? More production. There's environmental protection that costs 15. That includes preventing fertilizer from getting into the river and having permanent soil cover to prevent nitrogen runoff. There's something called best management practice methods or techniques which are most effective in preventing or minimizing pollution while making the optimal use of the resources. So that's sort of both water and pollution at the same time. It costs 10. Do we want to do that? Want to spend our money, or we want to build some more? Environmentally friendly, we confirm a change here. Let's see, down here we have settlement, a village. Here you can also do things. You can improve water quality standards, water conservation, sanitation programs. Water conservation? You want to do that? Conservation. Do we want to, and like that we can change some more. Do you want to build some more? We have money now. Build industry. I'm not hearing. Anything. Here is cotton. No, we made cotton, huh? Do we make some more cotton or no? Do we want to make groundnut plantation? No. What do you want to have? Food?
So energy. We need energy.
We need energy. Okay, let's make some energy first. You can have coal power. No. Wind power? Very nice. Wind power. We put some wind power here. It's going to take 1 turn to do that. You want... okay. Do we want to do any more? More food, more power, more what?
Dry season, it is dry season.
It's still dry, yeah? So we don't do any more? We run, okay. We run and hope for some more water. It has been claimed that more people have a mobile phone than have a toilet.
Is there any provision of undoing also? Let's say if I
No. Time only moves in one direction in this universe, I'm afraid.
no trial and error.
So we still have to develop 6 food farms and 3 cash farms. But now they also want 5 cottage industries, 2 mines, 3 primary processing industries. And it ends when we have reached 20 turns or have completed all these things, right? So we still have 6 food, 3 cash, 5 cotton, 2 mines, 3 primary processing. It's still very dry. Do you, yeah. Do you still want to build something? We are 4 turns out of 20 have run.
Because industries need water, so we can
Yeah.
that farmland should be the better one.
We could make a dam. Should we make a dam? Let's try that. It cost 100, so it's quite expensive. But with all this low water, I think that we need to find a lake somewhere.
Yes.
This is not a reservoir.
Here. Here.
Here you can place it. Okay, but it takes 2 turns before it's there. Do you want to? Okay, we just run.
Yes.
We run. We'll skip the background info here.
All that information.
Still dry. Yeah, what do you want to do?
Develop
Cash farm?
6 food farm.
Let's see, cash farm you say. And there's cotton or groundnut?
Which takes less water? Groundnut.
It's more or less the same. Groundnut, we put groundnut somewhere. It takes 2 turns before it's there actually. Do you want to build some more? Food farm again. Millet, maize. They like that in Malawi, but this is actually not Malawi. Maize somewhere here maybe. Okay. Any more? No? Run.
Money maybe should not buy pani
So still objectives are there. Also villages and towns now we need to make. The people are very demanding in this area, and we still have. The dam is not there yet. It may help once it comes. So, what do we do? More cash? How many cash farms did we need to make? Do you remember? 3. We have made 2, right? We have to make 5 what? Cash farms.
6 food farms and 3
3 cash, I think it was. We're a bit low on energy. Make some more energy.
So,
We have coal, wind, or gas. Gas? Somebody said gas, we put some gas. It takes 4 turns for that to work actually, so that's going to be a while before we see that energy. Anything else? We don't have much money, no? That's true. And power, and we have.
this time we would be having this.
The reservoir will be coming soon. Any villages, towns?
Yeah, but it's
Uh,
also very expensive.
It's expensive, yeah, we don't have that money. So we run again? Yeah, it's not easy, huh? We need some more rainfall. And maybe we should have started this gas power plant long ago, because it takes now 4 turns before we actually get the energy, and still we spend the money. Right? So globally, 1 out of 3 schools don't have water. We still have, it's still dry. Water is needed for cooling plants. It's running out. I don't know whether we can build more dams, but at least we have some money. Power is low, but that's coming eventually. Should we try to build more dams, or you want to, or maybe some water conservation? Let's see what we have up here. Maize, this maize farm, nothing was there. You want efficient water use? Let's see, here was a cash farm. Also efficient water use. What else do we have here? The millet. Same thing, or best management practice. Then you also have the environment. Maybe. Let's see, this one was power plant. You can actually also, I don't really know why, but also it doesn't cost anything, because a windmill should be fine, right? So we cancel that. Forest, but you can't do anything in it. Well, you could make it recreational and pest management, but again, that wouldn't do anything, right?